Hello everyone, my name is Jiro, and today I'll be presenting on technical computing with MATLAB. I'll be showing you how you can use MATLAB as a technical computing language and environment to solve an engineering problem. And the way I'm going to do this is because MATLAB is used in various application areas and industries, I'm going to talk about how MATLAB can be used as a workflow for solving such problems. So let's first take a look at what that technical computing workflow is. So regardless of which application that you're solving, you typically go through very similar steps in this workflow. So one of the first steps is to get access to the information that you're trying to analyze. So we call this the access phase. And that information can come in different forms. It might be a file that already exists on your computer, or it might be getting data from a hardware if you're doing some kind of an experiment. Or maybe you have data streaming from another software, or maybe streaming data from over the web. So regardless which source that you're getting data from, you first need to get access to that information. And then the core of your technical computing is spent in this middle area, which is to explore and get some insights to the data that you just brought in. So here you're making use of all the information, the expertise that you've gained in school, doing data analysis, modeling, or developing some algorithms. And then once you come to a conclusion, the final step doesn't finish there. The final step is to share that information, to communicate that finding in some way. So you might be creating a report, some write-up that describes the steps that you've taken, or maybe you're creating some application that might be used in another workflow. Well, the important part here is not that there are these three different phases, but that these three phases happen over and over again. It's not just a one-time process. You're constantly going back and forth between different phases. You might be getting new sets of data, or maybe trying out new algorithms. So this process becomes very iterative. So when things becomes very iterative, you want to start to automate the whole process so that you can easily move back and forth between different stages. So today I'm going to show you how MATLAB fits into this workflow and how you can use it to automate the whole workflow. Now before we actually get into the actual demonstration, let me just show you one possible deliverable of a problem-solving example. So here I'm showing you a report that illustrates all the steps that I've taken in order to analyze some particular data. So this is the case study that I'm going to be using. You can see in this report, I have divided up into different sections that correspond to the different steps in my analysis. You can see I have some visualization. And if you're familiar with MATLAB, you'll see that I have MATLAB commands that are incorporated inside this report, as well as any figures that the script was able to generate. Now, if I go all the way to the bottom, you see this report talks about all the processes. But at the very bottom, you see at the bottom that says this report was published with MATLAB 7.6. So what this shows is that this report was automatically generated from a MATLAB script that I had for doing the analysis. So I just pushed the button, and then it automatically generated the report with all the figures and the code embedded. So this is the end product that we'll be going to at the very end of this demonstration. Before we go into MATLAB and actually go through this example, let me just give you a brief background of what this example is, and just want to clarify that this is a case study that I chose to use to illustrate this workflow. Don't worry too much about the application. I'm just using this as an example. You can apply any sort of application that you're using and to fit this same similar type of approach. So this is a design optimization problem. The goal is to design a better engine cooling fan. So what you're seeing on this slide is as a picture of this engine cooling fan that sits in front of the radiator. The goal is to design a better fan for a new model of car that's coming out, which has a bigger engine, which generates more heat. So we need a fan that would output more airflow so that it'll cool the engine faster. Now we're going to go through several steps. We're going to set up some experiment to characterize the device, the fan, and then to find an optimal design that would give me the best performance. Now this is an optimization problem, so if we break it down to the core of the problem, we see that it has a design requirement. So this is the criteria they would like to reach, which is that we want this fan to output at least 875 cubic feet per minute. We'll see in a moment that the current fan does not meet this criteria, so that's why we have this problem. We also know that we have a few design parameters that we can change in order to improve the fan. One of the parameters is the distance from the radiator. The radiator sits, the fan sits in front of the radiator, and the distance between it we can vary from within the range of 1 inch to 1.5 inch. The next parameter is the blade pitch angle. Each of the blade is at an angle, and we can change that from within 15 to 35 degrees. The third parameter that we can vary is the blade tip clearance, which is the distance between the tip of the blade to the housing. We can vary that within between 1 to 2 inches. So we have these three different parameters that we can change to improve the performance of the fan. All right, so hopefully this the problem that we're trying to solve is clear. Now let's go into MATLAB and start solving this problem. So this is the MATLAB desktop. It's composed of various different components to make the interface a lot easier to use. And we'll introduce different parts as we come along in the demonstration. So if you recall from the workflow, the first step in solving a problem is to get access to some information, some data. What we have here in this current directory browser, a bunch of files, and one of them is an Excel file that says, it's titled original fan data.xls. Let me just open that up outside of MATLAB, so inside Excel. And we see that it's just a column data that shows the current airflow. So we have a current fan, and we just took 10,000 measurements of the current airflow just to get an idea of what my current performance is. And we see that the first first element, cell, has a cell heading called airflow. So that's the data that we're measuring. So we need to bring this data into MATLAB. Now there are several ways of bringing data, Excel data, into MATLAB. The approach that I'm going to take is to simply right-click and say import data. Now when I do that, MATLAB is going to take a look at the file and determine the best way to bring the data in by bringing up an import wizard. So it automatically detected that there's a column header named airflow. So it's going to bring in the data as an airflow with the variable name airflow. I'm also going to check the box down below that says generate encode and click finish. A couple things happen. First, the data was brought into the workspace. So workspace is MATLAB memory space, where any data that MATLAB knows about, it shows up in this workspace browser. You can see it's 10,000 by 1. It's a vector. I also generated this new M file. This is a MATLAB file, which has a sequence of MATLAB commands that will automate the process of importing. So when I imported using interactively by right-clicking and saying import data, now I can automate this process by simply calling this function import file, which is automatically generated from the import wizard. So let me save this out using the default name that I provided. Okay. Now, just to demonstrate, let me remove this data from the workspace. I can show you that by calling import file and specifying the name of the file, I have successfully automated this process of importing the data. And these are the steps that I'm going to be taking. I'm going to do a lot of work interactively, and then also have MATLAB help me automate the process along the way. Now we can see that we have the data. Now typically, the first thing that I want to do once I have data is to visualize, to get a sense of what this data represents. So I'm just going to highlight it and click on this button in the workspace browser to plot the data. Now when I do this, it gives me a default plot, and since this is a vector data, it just plots it as a line plot. You can see I have 10,000 elements, going from 1 to 10,000, and this graph represents my current airflow. You can see on average it's around 842 cubic feet per minute. And actually inside the workspace browser, this information is available. If I scroll over, the mean is 841.7. So we have the data, but now obviously I'm going to have to, I would want to improve this visualization a little bit, obviously add some labels, perhaps add some statistical information, maybe have a line that indicates what the requirement is. If you recall from the slide, our requirement is that we want the airflow to be at least 875. So maybe have a line that represents that line. So I'm going to modify this graph by opening up this interactive tool called Plot Tool. And when I do that, it opens up an interactive environment where I can customize the visualization. So I can first add some axis labels. So the X label is observations. Y label is airflow and cubic feet per minute. And then let's add some statistical information. So under the Tools menu, click on Data Statistics. And I want to add a line that represents the mean and standard deviation. And let me make it a little bit thicker so that it's easier to see. Okay. Now I also want to have a line that represents the requirement value. So let me add additional data to the graph. For this case, let me hard code the data. I want a line that goes from 1 to 10,000 at my requirement value, which is 875. So we have a line at the top, make it a little bit easier to see, make it thicker, and we'll change the limits so that we'll see all the data clearly. So now we can clearly see what the requirement is, give it a better name. And finally, let's move the legend outside of the graph. All right, so this graph looks good. I have very useful information. I can close out Plot Tools. And what I have is a nice visualization that gives me good information regarding my current airflow performance. Now that was fairly easy to do using the Plot Tools, very interactive. But if I want to automate this, perhaps for different sets of data, then I wouldn't want to have to go through the same interactive process because it takes some time. So I'm going to have MATLAB give me an automated code to regenerate similar graph. So I'm going to go to the File menu and click on Generate M File. What this is going to do is MATLAB is going to capture the state of the figure and give me a function that will allow me to regenerate a similar type of graph for any arbitrary data. So here's a new M file that MATLAB gave me called Create Figure, and save it out as the default name that I gave. Now, by simply typing Create Figure and giving the name of the data, and since in this case I hard-coded it, I'll type in the value for the requirement value, then I get back the visualization. Now one thing that you may have noticed is that, well, here's the auto-generated code, which looks very similar to what I had before, but here is the original one. One thing that you notice is that the limits are slightly different. I explicitly stated that I want my limit to go from 830 to 885, which was not honored in this auto-generated code. And this is purely because MATLAB wasn't quite sure exactly what your true intentions were in this auto-generated code. When I asked MATLAB to keep certain limits, MATLAB didn't know whether I chose that because of the particular data that I was plotting, or maybe I really wanted to be hard-coded in this particular limit. So in this case, what MATLAB did is if I look in this inside this auto-generated code, we see that MATLAB included the limits, but commented it out in this case. So there's a comment that says uncomment. So in this case, I really want to have MATLAB use this limit. So I'm going to just uncomment this line that says that gives the Y limit. I'm going to save it out. And in the meantime, I can also change this a little bit to make it a little bit more easier to use. So rather than having the user type in a vector coordinate, I'm going to have the user just type in a single value for the requirement. Then inside here, I'm just going to regenerate the data to be more flexible, and Y1 is the requirements. Save it out. Now, I can call this command again, but with a single additional argument. then I get back the visualization that I want. So what you saw is that I've used MATLAB's capability to interactively develop this visualization, have it auto-generated and encode, and then modify it to my particular needs. All right, so we've automated the import process as well as this visualization. All right, let's move on to the next step. We verify that our current fan is not meeting our requirement. So now we need to start to come up with a better design. Well, we know that we have these 3 different parameters that we can vary, but at this time I have no idea how those parameters relate to my airflow. So for instance, if I change the blade pitch angle to a higher value, is it going to increase airflow or decrease airflow? That I don't know yet. So I need to do some systematic experiment to understand the characteristic of my current fan. So I can do a very brute force experiment, build up some prototypes with different parameters and see take some measurements, or take a more statistical approach and do a design of experiments. So this is something that might happen often when you're working in MATLAB, that you know that there are some concepts that MATLAB can handle, but you don't exactly know the commands that are associated with it. So I'm going to search for that from the documentation, search for design of experiments, and see what MATLAB gives me. And when I do that, it gives me some pages from the documentation that has these keywords. And you can see the first few hits are from the statistics toolbox. And you can see that in the statistics toolbox, there's a whole section on design of experiments. Now, toolboxes are just add-ons to MATLAB that extends the capability of MATLAB for specific areas. Statistics toolbox extends the capability in the statistics area. Now, without going into too much detail, for this example, I'm going to use a response surface design of this design of experiments. And more specifically, I'm going to use the box Benkin design. So this is a way of coming up with a test case that I can go ahead and perform, and that'll give me enough information to build a good mathematical model of the device, or in this case, the fan. You can see inside this documentation there's several examples. Well, this example here actually applies to my case because I have a 3-parameter design. So if I evaluate this command, you can see that it gives me this matrix of numbers that represents the various experiments or prototypes that I need to build. Each row represents the different combinations. Each column represents the 3 parameters. -1 represents the lower bound. You can see, if you remember from the PowerPoint, each parameter had a lower and upper bound. -1 is the lower bound, 1 is the upper bound, and 0 is the midpoint. So what this says is that I need to build just these 15 different test cases, do an experiment, and then those 15 points are going to be enough to give me a good mathematical model of my fan. You can see there are a few repeated points for repeatability, but by performing these prototypes or building these prototypes, I can get a very rich set of data points for my mathematical model. I believe inside this example, there's another set of commands that will allow me to visualize it. You can just see that these points indicate the prototype, the test cases, meaning that I just need to build these midpoints of the edge cases of this design space. All right, so at this point, what I'm going to do is I'm going to switch over to a ready-made script so that we can step through the rest of the demonstration a lot quicker. But before I do that, I just want to show you how you might go about switching over from the workflow that you've been doing inside the command window over to a script environment. So up to this point, I've been using the command window exclusively. I've been typing commands. It's a nice environment to get some results right away. But at some point, I want to start putting together all these scripts so I can automate the whole process a lot easier. So what I can do is I can go over to the command history. The command history has kept track of all the commands that I've been typing, or MATLAB has been typing inside the command window. And I can just go ahead and select the commands that I want to use. So here's import, create figure, and then here's a set of commands for doing design of experiments. Right click and say create M file. All right. And MATLAB gave me a new M file that has just the commands that I had selected from the command history. I can save this out, and I'll call this my analysis. And this will allow me to automate the process up to this point. So let me just demonstrate that real quick. I'm going to clear out everything, and I'll call my analysis. It'll import the file. Create an additional figure here. Call my analysis again. You see that it creates visualization as well as the design of experiment, design matrix, design cube. So this is how I can start to build and create a final script that will automate the whole process of this design optimization. Now let me jump over to a final script so that we can step through the rest of the demonstration at a faster pace. And what you see here is that you see some similar commands. Here's the import file, a slightly different version of it. Here's an import file. Here's the create figure. And here's the box Benkin design. So I have the similar commands. Obviously, there are more commands down below, and we'll step through them in a moment. But you also notice that I have a lot of comments. So what you see in green, the one that starts with %, are comments, just for my own information. But also you see these double %, which creates the cell separations. So these individual sections are called cells in MATLAB. And these allow me to logically separate out the different sections in my script. One of the advantages of that is now I can start executing one cell at a time and then debug the different processes in my script. So for instance, if I start from my clean environment again, I can just click on this cell and click on this button that says evaluate cell in advance. And that would import the file, and it'll go to the next section and just wait for me to issue a different command. At any time, I can go to the command window, try out some different commands, or continue on with the next cell by just clicking on this button again. So you can see it allows me to easily work within a cell for a different section at a time rather than having to run the whole script from very beginning every time I change a small part of my script. All right, so we've gone up to this point already, which is the design of experiments, a slightly different visualization, which is the design cube. And now, in practice, I will go out and build those prototypes and make some measurements. I've already done this, and I have the results stored in another Excel file. So let me just open that up real quick. You can see that I went out and did those 15 experiments, and what you see in this Excel file is the 15 results. The first column represents the runs, so 1 through 15, and then the 15 results, the outputs. Now I can reuse this import file command to read in this Excel file. And then I'm going to also reuse the create figure command to visualize the data as well. Now what you're seeing here is the 15 data points, and again, the mean and the standard deviation, as well as the red requirement value. Now what you can see here is that of those 15 test cases, at least a few points meet my requirement. They're above the requirement value. So I know that there is a combination of the three parameters that will give me the required airflow. Now, a very crude way of finding the best point is just to pick out the best maximum point of this 15 test case. But there might be an even better combination that's even better than the results that are obtained here. So I'm going to use these 15 points to give me a mathematical model, and then I can optimize on on the best design. So at this point, I'm going to use those 15 test cases to build a mathematical model. And this is where you can decide what kind of model that you're going to use to represent this, this performance. In this case, I chose a full quadratic model, meaning I'm going to represent the airflow in terms of distance, pitch, clearance, the square terms, as well as the interaction terms. So distance by pitch, distance by clearance, and then pitch by clearance. So my goal is to find the 10 coefficients B0 through B9. Once I have that, I have a mathematical representation that represents the airflow in terms of the 3 parameters. I'm just going to do this by using the command from the statistics toolbox called the regstats command. Let's open up the help. And you can see that regstats is from the statistics toolbox. It performs regression. And also, it gives me several quantitative measures of how well the fit is. So one of them is R-squared statistics, which will give me a good idea of how well this model represents the data. So I'm going to run this and see what the R-squared value is. And we can see that the R-squared in this case is very close to 1, so it's a very good fit. Maybe in practice, if I was going to go even further, I might go ahead and do some stepwise regression to eliminate some of the parameters that are not significant. So instead of using this full quadratic model, I might do some statistics to take out some of the terms that are not significant. But in this case, I'm going to keep it as this full quadratic model. I have a pretty good model, a very good model, that represents a mathematical model that represents the airflow. Now, one way to interpret this model is to visualize it. So what I'm going to do is I'm going to take this model and visualize it and see how it looks in terms of the 3 parameters. So I've written a function here for visualizing, so just simply creating surface graphs. Then what you're seeing here is a visualization of airflow with respect to some of the parameters. Since we have airflow and then 3 parameters, I can't visualize all at once. I'm going to look at 2 at a time. So in this case, this graph shows airflow in terms of pitch and distance. You can see that you see some a dominant quadratic behavior here, that to maximize airflow, pitch has to be somewhere in the middle. That'll give me the maximum airflow. Same thing if I look at clearance and pitch. Pitch has a strong quadratic behavior here. Okay. If I look at distance and clearance, this is a lot easier to interpret. The maximum airflow is achieved at this corner here, which is a distance of 1 inch and clearance of 1 inch. So we have a pretty good idea just by visualizing this in 3D how to go about selecting the optimum point. Now, to be completely certain that we have the optimal design, we're going to go ahead and do an optimization routine using the mathematical model to find the optimum point for maximizing the airflow. So in this case, I'm not going to go into too much detail about the optimization routine, but let me just quickly open this file, which is again an auto-generated M file from the optimization tool that performs a constrained minimization routine on the model, so to maximize the airflow. So when we do this, it performs the optimization, has some animation that shows the optimization routine, and then the optimization returned to me the optimal values, which were the distance of 1 inch, clearance of 1 inch, and then pitch of 27.3 degrees. So this sort of agrees with the visualization that we had. Distance and clearance were supposed to be 1 inch, and then pitch was somewhere in the middle. And in this case, optimization found it to be around 27.3 degrees. If I again visualize that inside the using the design cube, the red point indicates the optimal combination of the 3 parameters. So in theory, this would be the conclusion. We found the optimal design, so we know exactly what the parameters are supposed to be to give me the best performance of the fan. But in practice, this is actually not the end. So in practice, we would take this parameter, take it to production, and have the production crew build a fan with these three parameters. But we know that in production, there's always going to be tolerance. There's going to be variability. They're not going to be able to build exactly to the specification that we provide. Or even if they can, if they're going to build thousands and millions of these parts, there's going to be some variability between the different parts. So as a designer, what we need to do is make sure that our design parameters are robust, taking into consideration the variability of the production as well as the model variability. So what we're going to do is we're going to do some simulation, taking into account the variability that might arise from production as well as the model variability. So what we're doing here is that we're going to create 10,000 simulation points, and what you're seeing here in the graph is a histogram of the 10,000 simulation points, all centered around the optimum points. So you can see the center point is 1 inch, 27.3 degrees, and then 1 inch. And this is a Gaussian distribution. Now we're going to run this simulation point through the model and then also take into consideration the model variability and see what the results give us. And then if we visualize it, what you're seeing here, now the blue points are now the simulation point, simulated points. You can see for the most part, they're above the requirement value. So we're sure that we're pretty confident that it's above they're going to be above the requirement value. If we look closely, we see a few points that fall below the requirement value. So we can even go one step further, study the distribution, and see what percentage passes the requirement. And this is what you're seeing here. Do some distribution using some of the tools from the statistics toolbox to give us a number, which is 99.8%, which will pass the requirement value. So now we have a pretty good confidence that our design parameters are going to satisfy our requirement value. All right, so at this point we've completed our analysis. We started from accessing our data, we did some visualization, and then we did some design of experiments to conduct some experiments, and then using those data points, we modeled the data, or modeled the current engine cooling fan, and then found the optimal design parameters that will give us a value that would meet our requirement. So the final step in our workflow is to combine all this information together into some deliverable. So we have, if we look through this script that we have here, we have a pretty good, well-documented script. Not only do we have obviously our commands, but we have a well-commented script with comments that describe what each of these cells are doing. The cells are divided up into different sections of our process. So we have a very well-documented script. We just need perhaps a better layout, a well-formatted deliverable that we can present to other people so that they can understand the process that we've taken. So I'm going to go over here to the toolbar. There's a button here that says Publish this M file. So I'm going to click on it. And what MATLAB is going to do is it's going to run through this whole script, execute one cell at a time, each cell at a time. It's going to capture any figures that it creates as well as any screen outputs. Then once everything is done, then it's going to put everything together into an HTML file, a report that I showed you at the very beginning. So right now we're just going through the whole script, creating all the visualization, and then as it's creating the visualization, it's just automatically capturing them. And then once it's done, you'll see that report that I showed you at the very beginning. So if you look at this, you'll notice that it's pretty much the same one that you saw before, but this was automatically regenerated when I clicked on that button. You can see each of the cell headings became the section headings, and this publishing capability automatically created a table of contents based on the cell headings. These are all hyperlinked to the various sections. You can see the MATLAB commands are there, as well as any figures that I created automatically embedded inside the report. So what this is a nice way of taking a script that does the work already, and then with a clickable button, it formats it and creates a presentable deliverable that you can give to other people. They'll be able to read through it and easily understand all the steps that you've taken in order to solve this problem. Okay, so let me switch over to PowerPoint and then recap what we have covered today. All right, so in today's example, as you saw, we went through these different stages in this technical computing workflow. We started off with accessing data from a file in this example. So we had a couple of files in Excel format, and we brought it in using the interactive way of bringing the data, and then have MATLAB automatically generate a code for doing this process. And then we spent some time within MATLAB to analyze the data, get some insights, do some modeling of the data, and then do optimization to come up with the best design of this engine cooling fan. And the output for the design will be taken to the next workflow, which might be the production workflow. But as we completed the work, we've documented the whole process by automatically just clicking on that button and automatically generating a report that shows the various steps that I've taken to do the design optimization. And throughout the process, you saw different ways of automating the process, either having MATLAB automatically generate a code or you combining different scripts together into a final script. So in this example, some of the tools that we use aside from MATLAB were the statistics toolbox for doing the mathematical modeling of the data, and then some optimization to come up with the optimal design of the engine cooling fan. All right, so this concludes the demonstration for technical computing with MATLAB, and hope you enjoyed the presentation. Thank you.